Hello, everyone. Welcome back to this week's Quantum Theory of Fields, Matter, and Strings seminar. Today, we are happy to have Markus Dierigl from CERN. Thank you for accepting our invitation. And he's going to be talking about exploring Utopia. You can start whenever you are ready.
Thank you very much. Thank you for the invitation. It's a pleasure to present some of my recent work here. So this work has been going on for quite a while, and I will mainly talk about this new paper that appeared on the arXiv recently in collaboration with Noah Brager, who just finished his PhD at UPenn, Aaron DeBray, who is a mathematician at Kentucky University, Jonathan Heckman at University of Pennsylvania, and Miguel Montero from Madrid. But it's also based, so I will sort of give an introduction using some earlier work together with Aaron, Jonathan, and Miguel. So please feel free to unmute yourself anytime, ask questions. I'm happy to answer, or also if you're interested in some things that I will not be too specific about, then just let me know and I can give more details. All right, so maybe let me start by just asking the question of what you would do if I give you a theory of, for example, this type. So if I give you a Lagrangian of Maxwell theory, so just a U1 gauge field that coupled with a kinetic term f mu nu with a coupling constant E. Right, so that of course is a very individual question, and everybody might have a different approach, but probably some of you would start writing down the equation of motion and solving them. Some of you would find that this f mu nu is actually a antisymmetric tensor that is divergence-less, so it would identify the Bianchi identities because of the antisymmetry of the partial derivative. Or later you might start, via canonically quantizing the U1 one-form field, you'll discover the photon and so on. Then nowadays, you might take a slightly different approach by specifying the different symmetries the theory might have. And of course, we know that the Maxwell theory, it has this gauge field A mu that has a gauge symmetry where you just shift your gauge field via the derivative of this gauge transformation lambda. And in modern language, this would be called a U1 zero form gauge symmetry. This is also encoded in this mathematical framework of a principal U1 bundle or differential cohomology, however you want to call it. And recently, this set of symmetries has been enlarged to also encode stuff that is not captured by local operators, such as this gauge field A mu, but is really supported by extended operators. These are the so-called higher form symmetries, or if they're more exotic, they are called generalized symmetries. And this Maxwell theory has them. And in particular, what you can see is you can shift your gauge field A mu by a flat connection. And the charged operators under that will not be point-like operators, but will be line operators, the so-called Wilson line. And you can do the same thing to the magnetic dual of the gauge field that couples to magnetically charged states. And you will discover the Toft line. So indeed, this Maxwell theory has two U1 one-form symmetries because the charged objects are these one-dimensional line operators. And so this is another different approach of how to understand the theory just by being given this Lagrangian. And at some point, maybe this Lagrangian becomes a little bit boring and you'll start adding stuff to your theory, right? For example, you can start adding charged fields as we would in electrodynamics or quantum electrodynamics, where we have the electron in our real world. And you couple it canonically to the gauge field with this covariant derivative like so. You might also include more exotic things like magnetic monopoles that would couple to the magnetic dual of the gauge field. And what you'll find is that the equation of motion get modified. So it's not the same as you discovered before, or the Bianchi identity might be modified if you add this magnetic states, this dynamical magnetic states. And at the same time, also the analysis using these channelized symmetries will be modified because the line operators that you had before, uh, importantly, they were not allowed to break, right? The charge was captured by closed or infinitely long lines. But now if you add this dynamical degrees of freedom, they can break. And associated to this is the breaking of the one-form symmetries, the electric one-form symmetry for dynamical electric states, the magnetic one-form symmetry for the magnetic ones. Of course, if you add your fermions in a particular way that has a chiral fermion spectrum, you have to also be aware of symmetry breaking via quantum corrections, so-called anomalies. So for example, if you add chiral fermions that are charged under the U1 in 4 dimensions, you will encounter these type of triangle diagrams that tell you that maybe your gauge symmetry or maybe some global symmetry like this chiral U1 can be broken due to quantum corrections. Okay. But in the end, all of what this is quite model dependent. So it's not very general, it's not universal, and it doesn't tell you about the full set of possibilities, but more about specific realizations thereof. So what instead of giving you this particular Lagrangian, I just give you the following information. I tell you I want to investigate a theory that lives in d dimensions, so d space-time dimensions. It allows for fermions. So in particular, I can, in principle, add the spin 1/2 fields if I want to. I don't have to. And it has this U1 gauge field in there. So it is a U1 gauge theory. Now, immediately you will discover that the possibilities are way bigger than just from the Lagrangian that I showed you before. Simply because now not only this kinetic term of your gauge field is something you can add, but for example, all of the powers of this. These are in 4-dimensional, non-renormalizable, but we didn't put any renormalizability in here. So in principle, they can be added. I didn't tell you whether I add electrically or even magnetically charged states. So these currents, the electric and the magnetic current might be there, or more general operators that respect this U1 gauge invariance. To make things a little bit more interested, I, on top of that, also want some notion of dynamics of space-time itself. So I don't want to constrain my theory to live on Minkowski space. I want to allow for more possibilities. However, I don't want somehow to get into all the problems of describing space-time itself at the smallest scale. So for me, it's still some effective theory of the space-time description where space-time is smooth. Okay. So what remains of what I did before? Of course, all the dynamics like the equations of motion, also the quantization. Now, of course, with gravity, that becomes harder because we don't know how to quantize gravity in general. And also the dynamical charges that you might have, all of them become harder to track because it depends on what kind of operators I really add to my theory, what kind of specific nature. But there is some general topological information that remains and that we can still understand with this very limited set of consistency or the limited set of information I want to put in. In particular, these anomalies, the specific anomaly will depend on the realization of the theory, but I can classify the potential anomalies in a very universal way. At the same time, there will be topological sectors of my theory that are also independent of the details of how and what kind of interactions I allow. And I can also specify like on which space-time manifolds at all I can define the theory that I'm interested in. Okay? And this will be the pieces of information that we're particularly interested in today. And just to give you a hint, let's go back to the U1 gauge theory. So we still have our U1 gauge field. Now I get rid of all the indices. I will move to this differential form notation because it's way shorter and more convenient. So the equation of motion is gone because I don't give you a Lagrangian anymore. I just give you a sort of a universality class of theories. But the Bianchi identity is still there because it just follows from the exactness or from the closeness of the field strength F. right? So the Bianchi identity is still there. And on top of that, I know that in my theory, this F has to have quantized values if I integrate it over a two submanifold of my spacetime. Right? That's what is known as the magnetic flux quantization, and it's really part of the defining data of my U1 theory, because F or the 1 divided by 2 pi F is the first Chern class, and it takes values in integer cohomology. In particular, if I look now at what this tells me is that I sort of have a conserved quantity, right? Because df is equal to 0. So if I take whatever two-dimensional submanifold in my space-time and I measure f, the integral of f through it, so if you want, if this is a space-like surface, then this would really be the magnetic flux through the surface. Which is quantized because of the quantization condition. I can deform this surface however I want, but because df is equal to 0, the magnetic flux measured after the deformation will be exactly the same as before. So in a sense, I cannot deform this part of my theory away. It's a conserved topological charge. Now, these conserved topological charges don't only exist in the gauge theory side, but also on the gravity side. And you can ask essentially the precisely equivalent question of, okay, let's start with a space-time that, for example, contains this two-sphere as part of it. Now, can I deform it into a different topology of space-time, like this two torus, or not? Now, if the answer is I can, then I would say there is no conserved topological charge that distinguishes these two space-time manifolds, right? Because I can smoothly deform from here to there, so I can change from this to the other sector. However, if I cannot, I would say there is now a topological charge that is captured by the space-time topology itself. Now, of course, there's a lot of information contained in what kind of spacetime I'm allowing for. And in particular, if I want fermions in the usual sense, I want my manifold to be a so-called spin manifold, so that it allows for the definition of fermions. I can also be more general. I might not be interested in fermions. Then I want maybe an orientation. Or if I'm interested in something like strings and their Bianchi identity, then I might be interested in a so-called string structure. If I want orientation reversal but still have fermions, I might be interested in pin structure, and there's a lot of things that you can do. Now, it seems like a very hard problem to figure out whether I can take one particular manifold and another one and ask, well, can I deform smoothly from here to there? And that's where mathematics helps a lot, because actually this is precisely the question answered by what is known as Bordism groups. So Bordism groups are precisely a classification of these deformation classes. So two manifolds are bordant, they're in the same Bordism group when they can be deformed smoothly into each other in such a way. And if they're not, then they define different elements of the Bordism group, different pieces. Okay, so in a sense, now this Bordism groups of the spacetime manifold, and this is the notation here. So this is a Bordism group of d-dimensional manifolds. So in this case, this would be two-dimensional, and this psi here sort of encodes what kind of demand I put on the manifold. So whether it has an orientation, a spin structure, and so on. And now in dimension 0 being smaller than d, being smaller than the number of spacetime dimensions, those precisely count my topological charges in the gravitational sector. Now, of course, ideally, I want to combine the two things. So I want the topological information in the gauge field as well as in the spacetime manifold. And this can be done by essentially now studying the different manifolds, so the two-sphere, but now also with a U1 gauge bundle on top of it. So now I have to specify the topology of my spacetime manifold and the flux, the gauge flux in it. And this is again captured by now a refined version of Bordisms, which has the same inputs as before. So it's the dimension of the manifold I'm interested in, the gravity part, what kind of information I want on the tangent bundle, plus now the information of the gauge field, which is captured by maps into the classifying space. But don't worry, just think about it as this tells you that I'm interested in deformations or manifolds that have a certain gauge bundle defined on it. And you can really think of it as part of spacetime, for example, in terms of this product manifolds of Minkowski space or a Euclideanized version of it times this compact d-dimensional space. It doesn't have to satisfy equations of motion or anything. This information we lost in the transition to topological properties, but contains this sort of very universal data. Now, one particular thing that arises also later, and I want to mention it here, is that actually these two parts might mix. So sometimes it's very convenient to separate what you demand on your tangent bundle, on your gravitational data, and what you demand on your gauge data. But sometimes the theory tells you that actually they're not independent and you have to define them together. And this will appear later, so I mention it here.
Can I ask a question?
Of course, yes.
Does this Bordism group capture the Toft anomalies of the theory? Like, is that encoded in the Bordism group?
Yes, I will come to that. Indeed, indeed it is, but not in the ones that I mentioned above, not in these ones, but actually in the ones that go to D+1, so capital D+1 and capital D+2. Those are the Bordism groups that capture the anomalies of the underlying theory.
I see. So you're talking about the anomaly theory. That is one
That's
dimensional.
right. That's right.
Okay.
So if it's a global anomaly or a Witten type anomaly, then you go to one extra dimension. If it's a perturbative anomaly that you would encounter, for example, in these U1 theories, then you go to the anomaly polynomial, which is D+2 dimensional. But I have a slide on this later. So this will not be part of what I discuss, but also is able to be captured by these deformation classes. Indeed.
Okay. Can I also ask another question? So when we fix small d to be capital D+1, is that related to the symmetry TFT that people talk about?
So it's in our case, it would be the anomaly theory. So it's not necessarily, it doesn't contain all the information. So I'm interested in sort of gravitational theories. So I cannot have relative theories. I always have the absolute theories. So I don't have this distinction. So in my setup, I will never discuss like going to this sandwich description where I define boundary conditions that then fix the symmetry type. For me, the symmetry type is fixed, and then I'm interested in the anomalies, for example, of the theory.
I see.
But yeah, the
Okay.
theories that we discuss are absolute theories and not relative theories.
Okay. Thanks.
Can I also ask a question?
Of course.
Why do the gravity and gauge part mix? Is it related to analytic torsion?
It's similar to that. So one simple example that you can imagine is you're allowed to violate this quantization condition in a sort of smart way. For example, if all my fermions in the theory have odd charges and all bosons have even charges under the gauge field, then I can get away by, allowing half integer fluxes, but the price I pay is that they have to, in addition, so only the fermions feel that because, they're the odd charged states. And I have to compensate for it by some gravitational information. So in particular, I have to make the theory consistent by whenever I have a half integer quantized magnetic flux, I have to put a non-trivial second Stiefel-Whitney class on the same cycle in a sense. And if I do that, I have to mix gravitational pieces of information with the gauge pieces of information. In this case, the structure that you get is a so-called spin C structure. And a similar situation will arrive later.
We have to compensate for. Okay,
exactly,
thank you.
Precisely, yes.
Can you go back a few slides where you discussed one form symmetry and its breaking by introducing matter?
Yes.
Yes, go one forward. Okay, I participated here to the talk. Actually, isn't the one form symmetry here, you said that it will be destroyed when we introduce matter. Isn't it more subtle than that?
In which sense? So what I'm saying is
Exactly. The reason I brought it up because exactly in the same sense as what you mentioned a moment ago. For example, let's say we have SUN
Mhm.
gauge theory, which has ZN one-form symmetry, and if I introduce electric matter, right, the ZN one-form symmetry will be broken,
That's right.
right?
Yes.
But if you when I introduce one-form matter, I also have a baryon number symmetry.
Right.
So then I can consider the quotient group SUN times U1 mod Zn, and actually I can turn on a U1 flux background and consider theory in something which looks like SUN mod Zn bundle,
That's right. Yes.
the other part. So there is also some similar interplay. This one-form symmetry is not completely gone in certain sense.
That's true.
Yeah, it reminded me of what you are saying in the context of gauge gravity.
Absolutely. Yes. So where this would appear, for example, if I would add more than one fermion, and I have additionally some type of flavor symmetry, then you can start playing games, right? Where I start mixing the gauge symmetry with the flavor symmetry by breaking some subpart, but then re-identifying it with a flavor and gauge
Yeah,
kernels.
that's one possibility. You can have flavor and gauge, and you can preserve. You can consider, gauge bundles which wouldn't normally live in SUN. And
That's right.
similarly, even with one fermion, you can do this trick with U1 baryon.
Yes,
And
yes,
the
indeed.
mechanism is very similar to the mechanism that you are talking now. You were talking a
Right.
moment ago.
That's
Okay.
right. That's right. So basically, what you're saying is I can sort of, I'm okay with introducing the obstruction of lifting a spin n mod zn bundle to a SUN mod zn bundle to a SUN bundle by also putting some flavor backgrounds if my fermions are charged under a flavor symmetry.
Exactly. Either flavor background or baryon
Yes.
number
I don't
flux,
I,
baryon
I I
number.
don't I don't want to consider this here. This was just for me was like whenever I have dynamically electrically charged particles under the U1, the original sort of the current equation, if you want, that the current star F is conserved,
Yeah,
is not true anymore. That is the only the message I want to convey. Of course, you can go to specific setups where things become way more complicated than here.
right, right. Okay. Okay. Thank you.
Welcome. Other questions? Okay, so here's the slide that I mentioned. So indeed, while we're focusing here on this small d between 0 and the number of space-time dimension, a lot of interesting things happen if you go beyond the number of space-time dimensions. And in particular, Bordism groups, the free part of the Bordism groups in d plus 2 dimension captures the perturbative anomalies. So perturbative anomalies means they're visible under infinitesimal gauge transformation, and sort of the discrete pieces, the torsion pieces in D plus 1, they capture the non-perturbative anomalies that cannot be seen from infinitesimal, but only from large gauge transformations. Okay, but this is just a sort of a brief excursion that Bordism groups can be also useful from that angle, but I'm not going to discuss it a lot here. So let's come back to the example. So remember, I only wanted to give you the following information. I want the capital D dimensional theory. I want to allow for fermions. So now this fixes my psi to be spin. So I want a spin manifold. And I want a U1 gauge theory. So I have this map to the classifying space of U1. Now D plus 1, D plus 2, they are the potential anomalies. So the classification of potential anomalies, of course, whether the anomaly is really there in the theory, again, depends, for example, on the chiral fermion spectrum or other chiral degrees of freedom. But this will capture all potential anomalies. And these small d, smaller than the number of space-time dimension, will be our conserved topological charges, so the information that we're interested in today. And also if little lowercase d is the same as the number of space-time dimensions, these Bordism groups are very interesting. So they're essentially associated to topological theories or topological terms you might add to your theory to modify it, and has a connection to what is nowadays called a -1 form symmetries. But also these will not play a role today. Okay, so the Bordism groups here are pretty easy to compute, and the following things arise. So in one dimensions, there is not much you can do. So the compact manifolds in one dimension is essentially unique. It's a circle. But since I have these fermions, I have one more extra data that the circle comes with. Namely, if I go with a fermion around the circle, I can come back to the fermion or minus the fermion. It turns out that actually this topological charge that is described by a Z2 is precisely captured by the circle where the fermion goes back to plus itself. And the reason is sort of easy to understand. So if something is trivial in Bordism, so carries no topological charges, I can describe it as a boundary. So think of it as like filling in the circle into a disk. Then I have a Bordism from the circle to nothing, so there is no topological charge there. Now, if the fermion has periodic boundary conditions, I cannot do that. Why is that the case? Well, think of the disk. Going around the boundary of the disk is a rotation by 360 degrees. And a rotation by 360 degrees on fermions always acts as a -1. So if the fermion, however, goes back to plus itself, I cannot fill the disk in. So that's precisely a topological gravitational charge that is carried by a circle with periodic boundary condition for the fermions. Now, if I go to 2 dimensions, there is a similar story. So now I have a 2 torus that has periodic boundary conditions for both of its elementary 1 cycles. That's also a gravitational topological charge, if you want. And I rediscover this factor of Z, which is precisely the quantized magnetic flux through the surface. So this is, again, we sort of anticipated that this will come out, and the Bordism indeed tells us there is a topological charge that is conserved and is described precisely by this. In 3 dimensions, there is nothing. In 4 dimensions, there would be interesting things. So if you're interested in 4D electrodynamics that are associated to theta angles, for example, U1 theta angles. And then there is nothing in 5 dimensions, so there is no global anomalies for 4D U1 gauge theories, but there is a bunch of perturbative anomalies. And if you know about the anomaly polynomial, these 2 Z factors are precisely associated to this pure gauge anomaly F cubed and this gauge gravitational anomaly F trace R squared. Okay, so sort of we really, from this very minimal input, we sort of get already quite a lot out of it, which is quite motivating. However, there is a problem here because I told you in the end, even though we now have this very minimal input, these universal features of topological charges and so on, we're interested in inherently gravitational theories. And there is evidence that in gravitational theories, there should be no global symmetries, meaning there should be no conserved global charges, also these topological global charges. Okay, so the reasons that why we believe that, they go back, for example, to black hole physics, where global charges, they don't cost any energy. So in particular, you can prepare a large black hole that carries, by throwing in globally charged particles, for example, and then you will evaporate into mainly the massless degrees of freedom, like photons that don't carry any global charge. And you're left with a very small black hole that has now an arbitrary global charge. Right, so now you have a black hole, a small black hole with essentially a free quantum number, and that violates the entropy bounds. Of course, there's some caveats, and you have to be careful in how to make these arguments, but this is sort of the upshot of how you do it. If you go into holographic setups.
Can I ask a question?
Oh, yeah, absolutely.
About the previous slide. So I was always wondering about whether this no global symmetries conjecture is valid for -1 form symmetries, because I don't think they have charged objects. So do we have this conjecture for -1 form?
As I said, I will not be discussing the lowercase d equal to capital D case, which would be the -1 form symmetries. I think there is a belief that So what would be the different theories with minus one form symmetries? They would be distinguished by essentially topological terms in the low energy effective action. And the belief is that there should be sort of a unique theory of quantum gravity, right? And if that is true, so I think the arguments are not as bulletproof as in particular for those zero form or higher form symmetries. But if you believe that there should be a unique quantum gravity, that there should not be the room for adding these topological
I see.
sectors. But it's an interesting possibility, and I don't think it has been answered sufficiently to state whether minus one form symmetries are allowed or not. So minus one form symmetry also are related to like free parameters, right? These theta angles. And if you believe that a well-defined theory of quantum gravity, so for string theory, we're pretty convinced that this is the case, but if this should be universally true, that it should not have any free parameters really, then I think the minus one form symmetries should be ruled out. Yes.
I see. But how can we, make a minus one form symmetry disappear? Like if you have a Lagrangian, by default, we have a minus one form symmetry.
That's right. So for example, if in this classification of this minus one form symmetries using the Bordism groups in the same dimension as space-time, you might, for example, argue that you restrict already on the level of Bordism groups. So you restrict your allowed space-time manifolds in such a way that you only take the ones where the theta angle doesn't have any influence. So it's sort of
I
an
see.
input. This would be what you would call a gauging procedure. The breaking of minus one form symmetries is probably a bit harder to understand.
I see. And if you do it topologically, then we have a quantum dual symmetry that is a D minus one form symmetry. Like we have to care about that as well if we gauge.
Right. So if we gauge the minus one form symmetry, what the quantum dual symmetry would be, I am not entirely sure. So
I mean, I think there would be like some domain walls in this new quantum dual symmetry, because it would be a D minus one form, and then we would have some universes, I guess, separated by these walls.
that could be the case, yes. So for example, this sort of happens, right? If you think about if I have the possibility of putting different values for a theta angle, then very naturally I can ask the question of like how does my theory behave if I define the theta angle differently in different regimes of space-time? And then the two will be connected via domain walls, which might be precisely the objects that if they become dynamical, they break the dual symmetry. But I'm not
I
entirely
see.
sure if this happens, but it sounds plausible. Yes.
I see. Okay. Thanks.
So if you go to holographic setups, this no global symmetries can become a bit more precise. In particular, having global symmetry in the gravitational bulk would violate the holographic principle because you can put globally charged objects inside the bulk and you wouldn't see them on the boundary. So they violate this bulk boundary correspondence. And you can do very specific calculations where you can also, for example, calculate the overlap of two states with different global charges, and you will find that it's non-zero in the gravitational theory, meaning that the symmetry has been violated.
Yeah.
Now,
Can I ask something about this?
yeah.
So can you have like extended objects that like connect two boundaries so that maybe they have some like remaining parts on the boundary CFT as well? Or is this like
So
something
there
plausible?
there is this paper by Harlow, I think it's earlier than this one, where he thinks about this two-sided ADS black hole, and then he asked like, what happens if I now have a Wilson line that goes from one boundary all the way through the wormhole to the other side? Now this looks like something that knows about both boundaries, which shouldn't exist. So he argues that one way to understand this is actually I have to demand that this Wilson line can be able to break, which means that I need to add this electrically charged particles inside the bulk such that I get rid of this correlation between left and right. This is one aspect of where two boundaries can sort of suggest that you have some completeness hypothesis in the sense that if you now have your line operators, they should be able to break via the inclusion of dynamical particles.
I see.
So what you see in all of these examples that the violation of the global symmetries should be at least of this order, like exponentially suppressed in the Planck mass. And this factor, if you think about the Planck mass as sort of the inverse coupling constant of gravity, tells you that these effects are non-perturbative in the gravitational regime. And we'll find that indeed this is the case. Okay, so let's now take this as a given. And then, of course, there is essentially two solutions of how to get rid of global symmetries. So one of them is, okay, maybe they're not global, they're gauged. Of course, you have to be very, very careful in gauging asymmetries. There might be precisely this violation via quantum effects, anomalies that cannot be there if you gauge the symmetry, but can be very predictive in terms of because they're invariant under renormalization group flow. You can do 't Hooft anomaly matching and all that. However, today I will mainly focus on the other possibility, which is the breaking of the global symmetry. So now the breaking of the global symmetry for me really means that there are physical processes or states that allow me to go from a sector of my theory that carries a charge q, global charge q, to one that carries a global charge which is different. Right? And if I can do this transition, then of course the charge is not conserved and the associated would-be global symmetry is broken. So in this sense, I'm talking about breaking today. Now, sometimes the effective field theory that I'm working with might not be able to do that, right? So maybe I need to add new things to my theory, some defect which is able to break the symmetry in the following way. So for example, I start with a sector of my theory that carries charge q, and then I add an object which from a low energy effective action might look singular, but still has a finite mass in terms of the Planck unit. So it's still dynamical within the full quantum gravity regime. And then suddenly I can change the charge to, let's say, q-1 if this has charge 1. And then, of course, I can just line up those objects, those symmetry breaking objects, and I can go to the sector where the global charges are 0. And then I can do this Bordism to nothing because now there is no global charge supporting it. And this sort of strategy or this sort of logic is what is at the heart of the so-called swampland cobordism conjecture. So that these transitions should exist for all consistent theories of quantum gravity. And of course, we don't really know what the structure of quantum gravity is, but we can do several approximations, which we'll do in the following. But then the Bordism groups here, they should all be 0 because all the global symmetries are characterized. The topological global symmetries are characterized by those groups.
Can I ask something on this?
Yes. Yes.
What will happen if the background is non-geometric? Like if we have fluxes or there was this paper last year by Tim Rase. They were considering a background as Landau-Ginzburg.
Right. So in our classification, we do assume that we have a space-time description with a smooth space-time. However, you will find that so we only do that for the supergravity approximation, and some non-geometric things will appear, as I will show later. In general, it can do also different things. So there has been papers by Yuji Tachikawa, where they don't really start from a space-time description, but they start from a worldsheet description. And of course, from the worldsheet description, something like Landau-Ginzburg, which doesn't have a geometric interpretation, is perfectly well defined. And then you can ask, like, can I do deformations within this worldsheet description? They did it for anomalies, not for the symmetry breaking objects or global symmetries, but in principle, a similar strategy would work for these global symmetries I will discuss today. And that goes beyond the smooth space-time geometry.
Thank you. Thanks.
Okay, so let's go back to the example. So I already showed you that there's a bunch of non-trivial Bordism classes. There was the circle with the periodic boundary conditions for the fermions. So in order to now cap off this circle, I need to include some object, some spin defect that allows for this transition. If I do so, actually, I solve the problem with the torus, because I can now basically edit inside of the torus, and I can also cap of the torus. So it solves two problems at the same time. And then I'm left with this generator in dimension 2, which is captured by the flux quantum. And I again have to add some object to it that allows my flux quantum and magnetic flux quantum to change. And of course, the magnetic monopole does the job, right? So if I add the dynamical magnetic monopole, dF is not equal to 0 anymore, and the topological charge is not conserved, right? Now, to come back to the point that I mentioned, in the low energy effective theory, however, the U1 magnetic monopole is really a singular configuration, right? It's not part of my principal U1 bundles, which is what I meant is sometimes you have to go beyond this EFT description. Of course, we know how to make this a nice configuration, for example, from going to U1 to SU2 and then breaking it, Topological monopole, and so on and so forth. And this sort of story where we have to add something that looks singular, but we sort of know how to resolve it in a enlarged theory will appear later as well. Now let's go to the first interesting sort of quantum gravity example, which is that of really the theory that we thought we understood best, namely, or one of the theories that we thought we understood best, which is just type 2b supergravity in 10 dimensions. And this is part of basically this 23 paper about tubordia, a map of which you can see here. Okay, so now let's ask, what is the input data? So what is the things we want to specify? So the input data for us will be the properties of space-time, as always. I want to have this topological pieces of gravity still around. And then I only want to add one more part of the information, which is the strong weak coupling duality of type 2b supergravity, which is also called S-duality. Now, funnily enough, in this case, indeed this mixing happens. And the reason is that the fermions of type 2b supergravity, they transform differently than the bosons under this S-duality. So now really this sort of spin C structure type mixing happens, and my geometrical data, namely the one of the spin manifold, mixes with that of the S-duality bundle. And what I have to specify is, so I can do different versions. I can either lift SL2C to its actions on the fermions, so that's a non-trivial extension, which is called the metaplectic group. But there is additional symmetry, which is I can flip the orientation of the string world sheet that would go from SL2, those are determinant 1, to determinant plus or minus 1. So there's also an orientation reversal here. Or I can do both things at the same time, which is this weird lift of fermions on a non-oriented manifold, which is a pin plus cover of GL. But you don't have to worry about it too much. So these are the most general versions that you can consider for your duality group, one without the orientation reversal of the world sheet and one with it. And this is sort of the input data that I showed you before. Now, of course, since we know that type 2b supergravity...
Can I ask a quick question?
Yes.
About the previous slide? Yes. So why are we gauging S-duality again? I missed this.
So S-duality is gauged because the theories are the same, right? So I basically can describe my theory in different duality frames, but there is no distinction between that. In another way, how you can understand it, sort of, right, is so if I wouldn't have gauged my S-duality, then the moduli space of my axiodilaton tau would be the upper half plane. But since I have gauged it, it's only this domain, sometimes it's called, I think, what is it called? The door lock, the keyhole region or something like this. So this tells you that you actually have gauged the SL2C because you identify the points on your moduli space if they're related via this transformation.
I see. Okay.
Now, since we know that the Bordism groups are associated to global symmetries, which are bad in quantum gravity, or anomalies, which are bad, they should all vanish. And since we also know that type 2b supergravity has a UV completion, namely type 2b string theory, what we expect is once we calculate the Bordism groups, all of them should be zero, right? Then you can sit down and you can really do the calculation, which is hard and uses some algebraic topology, namely spectral sequences, Atiyah-Hirzebruch, and Adams. But you can do it, and the result is this. So these are the Bordism groups for d dimensions. This is spin MP, so without the orientation reversal or with orientation reversal. And what you see there is not a lot of zeros, right? So in particular, in this range of lowercase d, you find a lot of potential global symmetries. So a lot of conserved topological charges. And this would also tell you that there's a lot of potential anomalies. Okay, so there is reason to worry. So I will not discuss the anomalies here. That is part of the 2021 paper, but I will focus on this global symmetries. But okay, I told you that this is not yet a reason to worry. Sometimes we just have to add things that were singular from the low energy perspective. And indeed, we know that string theory has a lot more ingredients than the supergravity. Just think of the D branes in my theory, right? So I wouldn't see them, but they might be responsible for getting rid of my global charges. So indeed, the type 2b string theory gives us a lot of things that we need in order to break the global symmetries. What is funny in some sense is that it always always pushes us into regions which are very interesting from string theory alone. So for example, some of the objects, the symmetry breaking objects in string theory that get rid of the global charges I showed you before are what is known as non-Higgsable clusters. So they appear in the construction of 6D superconformal field theories. They can be S-folds. There are funny theories that have this exotic n equal to 3 supersymmetry in 4 dimensions. Then indeed, the 7 branes are also there to break some of the symmetries and get rid of the global charges. And you find other topological twisted theories and so on. So indeed, string theory already takes care of most of the things that we would worry about because of the conservation of global charges and the associated global symmetries, but not quite everything. So there's one leftover generator, which is rather simple. It appears in this in the theory where we also include the orientation reversal, and it's given by a circle where you do this orientation flip, or better, it's lift to this pin plus cover when you go around it. So this cannot be capped off with anything that we know from string theory yet. So what we predict by that is for the associated global symmetry, which would be a Z2 global symmetry to be broken, you have to add a new object, which is a new 7 brane. And because it's related to the reflection, we called it the reflection 7 brane. And in its own right, it's a very interesting object. So it's SUSY breaking, the 3 branes can end on it, and sometimes it acts like a charge conjugation. But yeah, there is sort of this new highly non-perturbative object that should be there in string theory. Okay? So by very minimal input, we find in a theory that we thought we understood very well, a lot of extra ingredients were always pushed into interesting corners, and we even find like a new object there. So now, if you look at the map of Tubordia, you might start wondering, it's like, why is there a boat, and what happens in the east of Tubordia, right? Is there something we haven't explored? And indeed, it turns out there is, and it's what I will talk about in the rest of the talk, which is Utopia. Okay, so Utopia for me is now, let's go away from the 10-dimensional theory and start discussing lower dimensional supergravities with maximal supersymmetry. Right, so maximal supersymmetry means really 32 real supercharges. Right, and again, our input data is the theory defined on a particular spacetime manifold with all the requirements. And now the analog of the duality group, which is not anymore this the spin lift or pin lift of SL2Z, but is what is called U-duality. So it's larger groups. Unfortunately, we don't know this equivalence of the lifts of the U-duality group, which acts on the bosons that we know of, to the full fermionic version. So we'll stick to the bosonic version, and we have to take it with a grain of salt that we'll come back to in the end of the talk. And of course, another huge thanks to Paco for also drawing the map of Utopia here. Okay, now what is this U-duality? So in order to understand it better and somehow get a feel for it, we can ask, like, how does this lower dimensional maximal supersymmetric supergravity theories arise? And one way to construct them is to start with maximal supersymmetric theories in either 11 dimensions, so that's the M theory origin, or in 10 dimensions, then it's sort of a type 2b or type 2a origin, and then compactify without breaking any supersymmetries. So then we have to compactify on a K torus. And then the U-duality groups somehow are composed out of the large diffeomorphisms in the M theory. So basically, I can just redefine my fundamental domain of the torus in this torus lattice, or I can do T-dualities because, well, in string theory now we can essentially the size of a circle into the inverse, and I can do that because the winding modes of a string will exchange with the momentum modes, and it's a symmetry of the theory. Okay, so these are the two operations, but they don't commute with each other. So the U-duality group will be the group that is formed precisely by those two operations if I also do them simultaneously and respect the algebra that is imposed. And the result of that is these little funny looking discrete U-duality groups which take the following form. So there are these non-compact, for example, SL5C, or this E66, E77 exceptional kind of U-duality groups. Okay, and just think of them as composed out of both large diffeomorphism on the compactification of M theory and the T-duality of the parent string theory. So mainly we'll focus on this 8-dimensional case here. Those turn out to be very hard to keep track of from our calculational abilities, at least. Now, in 8D supergravity, so that is 32 supercharges, so is n equal to 2. The U-duality group is SL2Z times SL3Z. Okay, so this comes from large diffeomorphisms M theory on a 3 torus, and this essentially comes from the T-duality of type 2b on a 2 torus. Okay. Now this SL2Z factor already appeared in form of S-duality in 10-dimensional type 2b, and it's rather easy. The reason is that this SL2 essentially decomposes into a Z6 that is generated by this element and a Z4 that is generated by this S generator. Okay, this is an amalgamated product structure because, again, it's a infinite group, but it splits into these easier pieces that are also associated with special points in the moduli space. Now, the same structure, unfortunately, is not true for this other piece, the SL3Z, and has a way more complicated situation, decomposition into like a bunch of dihedral groups, symmetric groups, and so on. So what we're interested in is this now, as I told you, in principle, there would again be a mixture of this with a tangential structure because bosons and fermions transform differently. We don't know the precise form of that. So we'll stick to this bosonic version and we'll calculate the deformation classes of spin manifolds in D dimension with this bundle in SL2Z times SL3Z, the U-duality bundle. And once more, you can run your spectral sequences. And of course, there's thanks due to the fantastic work of both Noah and Aaron, who spend a lot of time and effort to really working those out. And indeed, you find again that not many of them are zero. In particular, none of them here in this range are zero. So again, all your alarm bells should go off, because in this range from 1 to 7, those would really correspond to now conserved topological charges in my 8D supergravity theory. Right? So 8D supergravity is not a UV complete quantum gravity theory. So you shouldn't worry too much now, because, well, maybe string theory has the objects. But then you can ask, like, what are the objects that are needed in order to get rid of these charges? What are the symmetry breaking objects? And for that, it's very useful to keep in mind this UV origin, and in particular also the UV origin the geometric origin of the different pieces of the duality group. So in particular, there is the origin of the M theory fiber. So M theory on a T3 geometrizes essentially this SL3Z factor. Now, if you do a type 2B or a F theory description, you can do a little bit more or complementary information. Namely, you can geometrize the SL2Z, which is the T2 compactification torus. I put my type 2B theory on it. And then I have a SL2Z subgroup of this original SL3Z, which is described again by this strong weak coupling duality. Right, so F theory captures a SL2 times SL2 subgroup of the full 8-dimensional U-duality group. And whenever we have this geometrical interpretation, it's sort of easy to work out what the objects should look like. So what do we expect? Well, we expect, of course, that we're now doing something that is a compactification of our 10D theory. So probably we should discover something that we already knew, but now compactified, right? This might be type 2B, F theory or M theory configurations. And probably those objects will also appear. We also expect that, well, sometimes if you have a higher dimensional object, I can wrap it, right? This was the same as in the spin Bordism. I had the two torus with both periodic boundary conditions, and I could use the codimension 2 object for the circle in order to get rid of the local charge. So an analog of this also appears in what we want to do. So we can basically bound one factor if our Bordism generator splits into 2 pieces via the defect that we already know, and then wrap it around the other factor. This also works for vibrations, but then it becomes a little bit more complicated. You get some sort of twisted topological twist or other twisted theories. Now, since we have the different UV descriptions, either the M theory origin, type 2B, or F theory origin, we can also ask the question is like, how do these defects distinguish between the different duality frames? And in particular, it will be interesting when the 2 factors that I showed you before, the 2 pieces of the U-duality group, namely the T-dualities and the large diffeomorphism, they start mixing, and I have to do both of them at the same time. Then there is no duality frame in which I really have a geometric interpretation, and indeed the defects are not geometric in the UV lift, right? So again, the bounding manifold in the supergravity is geometric. It's a smooth space-time, but the UV lift is not described by a geometric background, which is also what I answered to one of the questions. So non-geometry enters in our description because we have these T-dualities in the game.
Can I ask something?
Yes.
Since we have the dualities, what would happen at the, for example, self-dual radius for the T-duality? Because we know that there's a symmetry enhancement at that particular point.
Right.
Is there a relation between this and...
So sometimes, what we're often forced to is that, so think about a circle. Think about an 8D theory, and I just discussed something like T-duality. And I consider a circle in my 8D theory, and if I go around a circle, I do a T-duality transformation. So now I have a circle vibration where if I go around it, the circle goes from large values to small values of the radius. Right?
Like
So
F theory type of...
sort of a non-geometric F theory version.
Okay.
Then in order to have like a good geometry inside, it's often that on the singular point, you actually have to go to the self-dual radius of the string. So that is something that happens often.
Okay. Thank you.
Okay. So indeed, what we find is there's, for example, a Z3 factor in this lowercase d equal to 3 case, where we find precisely what we found in 10D, but now only compactified on a 2 torus. In particular, we had this non-Higgsable cluster, and now we can use the same non-Higgsable cluster and just compactify it on T2. If this T2 is very small, the low energy effective description is again interesting. So again, we're pushed into interesting corners. It's a so-called Argyris-Douglas theory, and it's sort of a descendant from Tubordia. At the same time, we have some other geometric M-theory configurations. That's a different Z3, which also have interesting corners because they push us into the description of what is known as 5D superconformal field theories coming from M-theory. And they live essentially on orbifold points of this type. So three-dimensional complex space divided by some rotational subgroup. And this geometry, if you have a closer look at how this acts, has precisely 3 of those points inside. So it's a partial compactification of 5D SCFT sectors. So again, string theory, or in this case, M theory, does the job and provides us with the object that allows us to change the would-be global charge. Now, starting at lowercase d equal to 5, we find some situations where we're forced to switch on both, like the T-duality transformation as well as the diffeomorphisms. So now there is no way in which we can describe it as geometric background in a lift to string or M theory, because I really have both the full T3 as well as the T2, and it's now a non-geometric defect, right? So now there is a sort of a prediction of a codimension 6 string defect, which is non-geometric in the UV lift. But again, it's not really something new that we have to add. It's sort of something that is integrated in string theory because T-duality can be modded out. So this would not be valid in any form of field theory because I really need this interchange of Whiting and momentum modes. And this is also sometimes known as this non-geometric backgrounds or T-fold geometries. Now, there is an attempt of doing something similar for these U-duality groups that you do for this S-duality in F-theory. Namely, can we sort of identify an auxiliary space-time, an auxiliary internal space that geometrizes the full U-duality group? Now, this includes a bunch of extra coordinates. So in 8 dimensions, the U-duality group is SL2 times SL3. And indeed, you need 6 extra coordinates. And sort of by cutting out slices of my 6D auxiliary space, I recover the original space-time in type 2B or M theory. So there's a question of what is the geometric interpretation of modding out T-duality? So yes, for me is if I go in at a particular point, so let's do it again for the SL2 S-duality. So if I am on an arbitrary point in my moduli space, so upper half plane modded out by SL2, right? The SL2 symmetry will be broken spontaneously by the value of the axiodilaton. Now, however, I can go to particular points, for example, tau equals to I, where it becomes invariant under part of the duality group. So for example, tau equal to I is invariant under the S generator of SL2Z. And at this point, I really discover this additional enhanced, not spontaneously broken gauge symmetry. So really, I think of the duality group as a gauge discrete symmetry in my system. And it becomes very, very explicit if I go to these points where some of the generators act without changing anything. I hope that answers the question. Okay. Now, whether I cut out...
Is there any bosonic field associated with this non-spontaneous symmetry breaking?
So you can ask sort of Yeah, so it's a good question. So if you do the axiodilaton, for example, you can see that only the PSL2Z group acts non-trivially. So in particular, if you take the -1, it acts trivially on tau. So you would not be able to distinguish that. In the full bosonic field of the theory, that's no longer true because the -1 in type 2B will act on the two form fields. Like the Neveu-Schwarz and the Ramond-Ramond two form, they will get a minus sign under this transformation, therefore are not invariant anymore. So indeed, in that case, since, however, I can always switch off the two-form fields, the point where the two-form fields vanish and the axiodilaton sits at the point tau equal to I will still have this full Z4 subgroup of the SL2Z as a non-broken gauge symmetry. But it's a good point that other fields might see more of the duality group than the axiodilaton does, for example.
Thank you.
Okay, so and then you have this sort of constraint in how to cut out slices that describe your non-trivial space-time manifold that is not part of the auxiliary space, but now really of space-time. And right, so there might be the hope, and I will show one picture later, but it's not really too deep. There might be the hope, and maybe we can use this exceptional field theory jargon in order to get a better understanding, a more geometric understanding of this symmetry breaking objects which are non-geometric in M or type 2B theory. All right, so let me maybe just show you a couple of surprises. So first of all, first surprise is that actually the codimension 2 objects, so those would be predicted by the one-dimensional Portism group, right? Because I have to close the circle and put the object. So codimension 2 comes from this circle pieces. It's actually very sparse. In particular, I get the Z2, that's just from spin Bordism. We already discussed it. It needs the spin defect. And then I get the abelianization of the U-duality group. Now the abelianization is 0 for SL3. It's a Z12 for SL2. That's why we found something interesting in 8 dimensions. But in all higher dimensions, the abelianization of the U-duality group is 0. So actually, there is no extra defects needed in codimension 2. However, that is not to say that the objects that would be the ones that have a monodromy in the U-duality around them are not interesting objects. They're so-called exotic branes and were discussed for various reasons, including black hole microstates. So they're interesting. They're just not needed in order to break the global symmetries. You can ask the question, why is that? Well, there is a configuration that doesn't have any singularity. It's a nice, smooth configuration. It still bounds the circle with a transition function. And what it is more like a gravitational soliton or wormhole-like configuration. So the would-be generator is again S1, where I go around it and I have a U-duality transformation. So let's just denote it via this dot that implements the transition function. Then the typical singular object solution is, okay, if I include an object where my partition function can end, I can cap off this geometry and my problem is solved. However, if the transition function or the element that defines the transition function is a commutator, I can do the same thing without a singular object for the price of having a non-trivial space-time topology. Right? So if G is the commutator, I can write it like this, and then I can use this internal one cycle in order to produce this commutator around the circle. And as you see, there is not anymore anything where transition function end. There is no geometric singularity anymore. So it's not really a new singular object I have to add. My smooth supergravity has all the ingredients I need. And indeed, you see what I said before is you expect at least the symmetry breaking effect to kick in non-perturbatively in terms of gravity. And this, because it has now this non-trivial space-time topology and it's like a solitonid object, is what I would call a non-perturbative breaking via gravitational soliton. So it's exactly what we would expect to happen. Now, however, there's a surprise. So in d equal to 2, we find a generator that looks as follows. So it's just a 2 torus with 2 transition functions around the 2-1 cycles. Again, I draw them in terms of these lines here. But both of the transition function, they're both sit in SL3Z. And I just told you SL3Z, the commutator subgroup generates the full group. So the abelianization is trivial. So how is it possible that I find a generator like this? I just told you that if I have a transition function with SL3, I find a gravitational soliton. So why can I not use it here? And the reason is the following. So let's try to do what you might do. It's like I just told you how to bound the circle with a transition function with a gravitational soliton, right? But then if I go around the other S1 of the 2 torus, I have to cross a transition function. That's the one on the other cycle. And the elements here that constitute the commutators, they're not invariant under this action of the transition function. Right? The combined element, the commutator of G1 and G2 was, so the singular object does the job and everything is fine. But the gravitational soliton is just not a good configuration in this background. And that's why sometimes, and it was really a surprise for me, sometimes sort of the solution you had in a certain number of dimensions doesn't work anymore because the other transition functions that you need to implement will not leave the gravitational soliton invariant. So sometimes you cannot solve the same using these configurations. Now, another surprise is that we find a lot of SCFTs with a twist, in the sense that now if you have an M-theory fiber structure, where M-theory fiber is the 3 torus, we encounter situations where the singular fiber becomes something like a 2 torus orbifold. So this would be T2 mod Z3, fibered over an additional circle. And this sort of leads to a twist of different superconformal field theory sectors into each other and has a quite interesting structure that we didn't expect from the get-go. But again, string theory sort of gives us all the ingredients we need in order to get rid of the global symmetries. The same is true for these compactification cases where sometimes the Bordism generator is a vibration. So we find non-trivial topological twists and also non-trivial non-geometric bundles. So again, we find sort of situations where I have a geometric object that I have to put on a space with a bundle which is not geometric from the perspective of the object. So we called it a non-geometric twist that naturally appears in this setup. And finally, what I want to mention is this is not the full picture, because I told you I only had control over the bosonic version of the duality group, but we know that it's not the full story. And it's simple to see in a sense, because I can always go to a point again where T2, for example, sits at tau equal to I, and then S becomes just a rotation by pi half, right? And therefore we know if it acts like a rotation by pi half, the action on fermions will be different than on bosons. So in particular, S to the 4 has to act with a minus sign. So there should be some version of this spin plus lift or spin GL plus structure, which will hopefully work out soon and then reconsider. Because we know that the same happened here in type 2b in 10 dimension. And if you compare, for example, this is the bosonic version of the duality group, and this is where we do the spin lift, you can see that there can be quite different groups appearing here. Sometimes you get less, sometimes you get more, and sort of it is quite obvious that you have to be very careful in how to treat those objects. So this is something that we hope to come back to in the near future. However, maybe the biggest surprise is that not like in 10 dimensions, we don't need to add anything new. We have to consider very interesting and exotic backgrounds. That's true. So this gluing using T-duality, so non-geometric situations or generalization thereof. Maybe we have some some notion of this exceptional field theory intuition where we still can geometrize the defects that we're interested in. But the string theory has everything we need. So once we go from once we go from 8D maximal supergravity to its string completion, then we don't have to do anything in terms of adding new objects like the R7 brane. But it really has to use the stringy ingredients because there is T-duality in there that is has this very stringy origin.
Markus, I have a remark.
Yes.
I think philosophically you are saying something very nice, very interesting, but I think to my taste you are phrasing it a little bit differently.
Okay.
What I want to say is following. You say, hey, I have supergravity, with all these symmetries, but I know that and you are using this deformation class idea.
Yes.
And you are saying, what kind of objects do I need to get rid of all of these symmetries?
That's
Then
right.
it points you to the set of objects. And you are actually, think of the following world. Let's say you did not discover string theory. Okay, but you were only playing a deformation class game with the supergravity.
Absolutely.
Okay, it
Yes.
would tell you that these objects has to be there.
That's correct.
I think this is very, very, very nice idea in certain sense. I mean, this deformation class idea.
That's right. So
yeah.
So you want basically you want me to stress more that the classification actually has nothing to do with string theory. So I would have to add those objects regardless of the UV completion. It just turns out that string theory, if I do the UV completion in string theory, already has the ingredients that I need, right?
Yeah. The point is you would produce all non-perturbative objects in this string theory through this.
That's right. That's right.
So you would, in some sense, yeah. And you can even say things depending on your symmetries and how you lift them. It depends on which type of theory you are. You may even come up with things related to dualities. I think I like this deformation class idea a lot. So I just wanted to make this remark. You are sort of predicting the objects of the string theory.
That's right. That's right.
Yeah.
And indeed, as we showed in type 2b, there is even new things that we didn't know about, right? There's now a new 7 brane in the game in some sort of sense.
Exactly. And again, I knew this deformation class idea a little bit in the context of condensed matter. This is exactly its utility. It's a quite remarkable tool.
Yes, I agree.
Yeah.
And yeah, so with that, I'm already over time, but I was told that that's okay. So let me just summarize. So as in the story for Tubordia, so type 2b in 10 dimension, this boardism, this deformation class approach is really able to predict many new symmetry breaking objects that are imposed by the breaking of symmetries. And what is also remarkable on top of Mithat said is that somehow, even though we know that these objects sort of are contained in string theory, they're always pointing towards interesting sectors, like the superconformal field theories, these twisted theories. So somehow there seems to be a very rich class of backgrounds that are there for us to be discovered and studied, sitting in this deformation class approach. I should mention, however, that of course also the way we construct the generators is biased by our understanding of string theory. So it doesn't mean that I couldn't choose any other boardism generators because they're topological. They might be very, very different. They might break supersymmetry completely and so on. But still, if I do the minimal version of I try to preserve supersymmetry as much as I can, I'm always pushed into these interesting regions. However, there's many things to do. Maybe most pressing is the issue of the fermionic lift. What kind of new topological charges emerge? What kind of other topological charges disappear? And then, of course, it would be interesting to also dig more into the properties of the defects themselves. So now we have sort of an understanding what they are, but since we know that in some cases they're associated with very interesting world volume theories, like superconformal field theories in high dimensions and so on. Is this true also for these non-geometric defects? And one thing I want to point out is that this is also an area where the physics and math really are sort of go hand in hand, in the sense that physics often can give a lot of intuition in determining the deformation classes and their interpretation. But also you need new math in order to figure out or verify your ideas in string theory or quantum gravity and the topological charge business. And with that, I want to thank you for your attention. And of course, if you have more questions, I will stick around.
Yeah, thank you for this wonderful presentation. I think everyone learned something new. I mean, you had lots of pictures and intuitive explanations. I think everyone at least understood some stuff. So if
I'll
there
be
are
very happy, yes.
any questions we can ask, I mean, if the people are not comfortable with the recording, we can also turn off the recording and maybe then some people would like to ask questions.
I have a question actually. Since we're introducing new ingredients, or at least a few unknown ingredients to string theory, we know that, for example, scale separation is very highly dependent on whether there's some orientifolds in the theory or not. So what do you expect these kind of studies would give objects that are related to scale separation? And do you think there's a relation between the cobordism or broken symmetries or cancelled anomalies between this and scale separation?
So that's a tough question because in some sense, yes. So for example, if you include the orientation reversal, we find that some of the Bordism groups are associated to, or the global symmetries associated to them are broken when we include, let's say, O5 planes. So orientifold planes are already in the picture somehow. But the problem is that we never really solve any equations of motion. We're only considering topological properties. So none of the solutions, well, the supersymmetric ones, they are solutions to the equation of motion because they're BPS. But in principle, all the generators that I can write down, they don't have to be. Only the topological properties have to be correct. Now, in applications to scale separation and all this, it's very important that you have objects where the tension, for example, is negative, as the O7 or the O5 happen to be, but it's very hard to see that from the Bordism approach. So from the Bordism approach, the important piece of information is that the O plane somehow flips the orientation of the world sheet when I go around it. So we're thinking about, and I'm thinking about a way to somehow extract more, starting to extract more dynamical data out of this topological approach to Bordism classes. But for that, you would have to go beyond the discussion that I showed today.
I know that there are some papers regarding cobordism classes and end of the world brain type of dynamic classifications from Madrid people and from Munich, but
so
those are like.
So their approach is a bit basically going the other direction. So
Yes.
what they're doing is they specify like, okay, I take a theory and I study configurations where space-time ends in some sense. So I really do a dynamical analysis. I solve the equation of motion and I have a point which is at finite distance, right, where my space-time ends. And then I think it's a very reasonable assumption to assume, and they don't write down what kind of Bordism group they're associated to, but it's sort of a reasonable assumption to say like, okay, probably this is necessary in order to get rid of some global symmetries of the theory.
But there was a paper from Blumenhagen and Nicola Cribriori. I believe in that paper they were mentioning some cobordism classes for this.
So sometimes you can ask the question is if you include objects in your theory, can I then still extract some information? So They tried, I think, to connect essentially the spin C structure that you get on the world volume theory of D branes with a Bordism group of the bulk theory, which doesn't have a spin C structure because there is no U1 field in type 2b, for example, but to make a connection between the two. Now, that's also a very interesting question. So often there is like a map between Bordism groups of space-time and submanifolds of space-time. So this is called Smith homomorphism. And you might ask, like, okay, what kind of information can I extract from these maps between the different branches? For example, can I really see that if I include 7 branes, I can get particular backgrounds that kill the Bordism classes of my type 2 theory, and so on and so forth. So there's a very rich structure there that relates the two. Again, whenever you use Bordism classes, the information you have is inherently topological. It's a cohomology theory. So it's not sensitive to the solution of the equation of motion, but since you're specifying a topology, right, you're certain that there has to be a minimal action or minimal energy configuration within this topological class. And then you can ask which is it? And in the situations where you preserve supersymmetry, you're confident that you found at least a version of it. But whenever, for example, for the R7 brane, you break supersymmetry, it becomes very hard to start extracting dynamical information like the tension of the brane. And indeed, we could not. So there is some bounds that you can put, but yeah.
Thank you. Thanks.
Can I ask a question? So you were talking about gauging dualities a couple of slides back. What I don't understand is, so I understand that you identify dual theories like gauging, but usually when we gauge a symmetry, we turn on some background field and then take a sum over these fields. Can we have a perspective in which we are turning on some background field or something like that, and then summing over the path integral? Like,
Yeah,
can we
I
think
think
of the gauging duality in this sense?
Yeah, I think so. So for that, of course, as I said, so typically if you go to an arbitrary point in moduli space, the duality symmetries will be broken spontaneously, meaning they will be broken by the background values of fields like the axiodilaton. Now, if you go to particular points, the part of the full duality group will be restored, right? And in those points, I think you can really understand it in terms of the identification or an honest gauging, summing over the different bundles of your theory that should make sense. So for example, if you go to this tau equal to I point, and let's say you switch off all the other fields in your type 2b, then you get a full Z4, or if you go to the spin lift, a Z8 of symmetries that is restored and that I can now really describe as an unbroken gauge symmetry in my system. And again, the way to understand it is like in string theory, we have no preference for the duality frame, right? So that it's really sort of a gauge degree of freedom in what kind of duality frame I describe my theory. So it's really it doesn't contain any physical information. One might be smarter than the other. In particular, if you break some symmetry spontaneously, but there is no preference a priori. And this is sort of represented by this gauging procedure.
I see. Okay. Thanks. I can turn off the recording if people want to ask questions off record. Okay.